Alright, welcome back friends. Today we are going to look at molar volume. We've looked at molar mass, we've looked at moles, now we're going to look at molar volume. But I did want to do a quick recap, just since we have had such crazy schedules lately, and with me being gone, I wanted to kind of take a look at the big picture. And we had talked about this analogy in class a couple times. And I had talked about a metro system or a subway where you have to, take one line into a central station before you can change trains and then make your way out to another line to get to your final destination. Your book has an interesting figure here. If we can see, it kind of looks like a flux capacitor for all of you Back to the Future fans out there. But it's basically just looks like it's three roads that intersect in one big intersection, right? Maybe something they're thinking of putting out in West Bay at the bypass there. But essentially what they're trying to show you again is that you've got moles here in the center, and that in order to move from one of these, such as mass, to one of the other ones, such as representative particles, you can't just go straight across. You have to go to moles, and then from moles back out to here, or from representative particles to moles, and then from moles up here to volume of gas. So it's kind of a nice figure to illustrate what I was talking about in class. Now, we've covered most of this. So we started with atoms and molecules, and we didn't talk a whole lot about this term representative particles. Basically what it means is whatever that particle is. So if I say I have a mole of carbon, well, that's going to be carbon atoms, right? Individual atoms, because carbon is an element. But if I say I have a mole of water, well, I'm going to have a mole of molecules, because water is a molecule. So really it just is whatever particle that thing is made up of. Now you have to be careful, because if you think about 1 mole of water, that has 6.02 times 10 to the 23rd water molecules, but each water molecule is made up of 2 hydrogens and 1 oxygen. So if you think about the number of atoms that are in 1 mole of water molecules, it's actually 3 times that number, because for every molecule, if you have a mole of the water molecules, each molecule is made up of 3 atoms, 2 hydrogens and 1 oxygen. So you have to be careful with the way that they word things. You really have to read the questions carefully and be on your toes. Now we can see examples of all of these different things. So the first thing that they talk about, if we were to look at converting atoms into moles. And so I'm not going to take a whole lot of time, because you can read through this. These examples are straight from your textbook, but essentially we're using Avogadro's number, and we're going to set up a conversion factor. So here we know that 1 mole of magnesium is equal to 6.02 times 10 to the 23rd atoms of magnesium. And they've got 2 conversion factors here, right? 1 mole over that many atoms, or that many atoms over 1 mole. And we have to decide which one is going to be the one that we want. Well, if we come down here to our problem, we're starting with the number of atoms, right? The problem tells us 1.25 times 10 to the 23rd atoms. So we're starting with atoms. So if we look at the conversion factor, we need to choose the one that has atoms in the denominator so that it will cancel, and moles in the numerator, so that that's the unit that we're left with. So we do want to choose this one to the left, so that the units cancel properly and we get our correct answer. So there's just a matter of dividing by Avogadro's number. Again, so that's if we're trying to go from the number of particles to the number of moles. Notice this road here has 1 mole over Avogadro's number of particles. So they're telling us that that's the conversion factor that we would use if we were going from particles out to moles. So if you really wanted to memorize this figure, it could help you out quite a bit. Me personally, I just like to look at, okay, what unit do I need to cancel, what unit do I need to introduce, and then think about it that way, because it makes it much easier when you move into problems later that have 2, 3, and 4 steps in them. If we continue on, another example, now instead of going from atoms to moles, we're going from moles to atoms. So this time they give us the number of moles that are in propane, the number of moles of propane, C3H8, and they want to know how many atoms. Now here, this is again one of those tricky ones where we need to read. They're asking about atoms, but they're giving us moles of propane, which is a molecule, right? Every molecule of propane has 3 carbons and 8 hydrogens for a total of 11 atoms. So if we see that here, we can see that 1 mole of propane is actually equal to 6.02 times 10 to the 23rd molecules of propane. But remember, 1 molecule of propane is actually made up of 3 carbons and 8 hydrogens for a total of 11 atoms. So we have to be careful. The question does ask for atoms, not for molecules. If the question just asks us for the number of propane molecules, we could just multiply by Avogadro's number, right? So if we look down here, we start with 2.12 moles. If we were to multiply by Avogadro's number, the number of moles would cancel, and we'd be left with the number of propane molecules. But that's not what they ask. They ask for the number of atoms that are in there. For that, we need to go one step further and note that there are 11 atoms in 1 molecule of propane. 3 carbons and 8 hydrogens. So there our molecules cancel, so we're just multiplying by 11 to get our final answer. So again, that's if we're going from moles out to particles. And notice they again give us the conversion factor. We're essentially multiplying by Avogadro's number to get out to the number of molecules or atoms, whatever the representative particle of that material. And then we also talked about mass. So earlier today in class you did quite a bit of practice on calculating the molar mass of different substances, whether they be straight elements, which are easy, we just find it on the periodic table, or if it's something that's a little more complex, still not that difficult. We just look at the number of atoms of each element, add up everything to find the total molar mass. So if we look at an example here, now we're going from moles to mass instead of moles to particles. So we do need to determine the molar mass. So they tell us that we have 9.45 moles of aluminum oxide. And they also give us the formula, so that helps. We don't have to balance that. They've already done it for us. And they want to know the mass, right? It says, what is the mass? So in order to do that, if we want to go from moles to mass, we need the molar mass. See how it's right there in the name? Pretty clever how they did that. So to figure out the molar mass, we can see that aluminum oxide has 2 aluminums and 3 oxygens. Okay, now if we have 1 mole of aluminum oxide, that means we have 2 moles of aluminum atoms and 3 moles of oxygen atoms. Does that make sense? If this is 1 mole of the whole thing, right? If I had 5 cups of jelly beans and each cup had 2 green jelly beans and 3 red jelly beans, then I would have a total of 2 times 5 green jelly beans, I'd have 10, and 3 times 5 red jelly beans, that would be 15. Same thing here, if I have 1 mole of aluminum oxide, that means I have 2 moles of aluminum atoms, 3 moles of oxygen atoms. So if I'm looking at the molar mass, right, if I have 2 moles of aluminum and there's 27 grams in 1 mole of aluminum, that's from the periodic table, then I'm going to have 54 grams of aluminum. And if I have 3 moles of oxygen, 16 grams of oxygen per 1 mole, again, straight from the periodic table, I have 48 grams of oxygen. Put all of this together, add the 2, and I get 102 grams of aluminum oxide in 1 mole of aluminum oxide. So there's my conversion factor now that I know the molar mass of aluminum oxide, and it's just a matter of multiplying, right? If we look at our conversion factor, we put moles on the bottom so that they cancel here. We put grams on the top, multiply through, we get our final answer. Again, so that's if we're going from moles to mass, right? If we're trying to find the mass. We can also look at this if we were to go in reverse, right? If we were to go from mass to moles, we could do that as well. In this case, they give us iron 3 oxide, and they want to know how many moles of it there are in 92.2 grams. So again, we're going to need the molar mass. Anytime we're going between mass and moles, regardless of the direction, we're going to need the molar mass. So again, if we work this out, if we have 1 mole of iron 3 oxide, then we're going to have 2 moles. So they've balanced it for us, so we don't have to do it. We've got 2 moles of iron, 3 moles of oxygen. So 2 moles of iron multiplied by the molar mass, We get our total, 3 moles of oxygen multiplied by the molar mass of pure oxygen. We get 48, add them all together, 159.6, and there's our conversion factor, right? The actual molar mass of this substance, iron 3 oxide, 159.6 grams of it per 1 mole. Now that we have this time we're going from grams to moles, so we want grams to be on the bottom, we want moles to be on the top, right? And grams cancel, we're left with moles, and we get our final answer. This time we're dividing instead of multiplying. So that's given us our last, before we went from moles to mass, that example we went from mass to moles. So the only thing that we have not yet covered is this area up here with volume of gas. Now there's a reason that we kind of saved this one for last, because it's not quite as intuitive. We have to think about it a little bit. The conversion is just as easy as the other ones, if not easier, because the number is smaller. It's not as big as Avogadro's number, and we don't have to work it out like we do the molar mass. It's always going to be the same. But there is a little bit more of a conceptual learning curve that's involved, and it actually is Avogadro again, but this time it's Avogadro's hypothesis. And if you think about two gases in a container, right? Obviously they've made these much bigger than they actually are because you can't see individual atoms or molecules. But if we were to think about these blue molecules and these red molecules, and the blue ones, maybe those are individual atoms, and maybe it's argon gas or something like that. And the red ones over here, maybe they're something bigger. Maybe they're sulfur hexafluoride, right? Something that's going to be a lot bigger. But if you look at the relative size of the actual molecule or atom as compared to the container, it's very small. Remember, gases spread out, so these things are going to be sort of bouncing all over the place. So the actual size of the atom or the molecule really doesn't take up a lot of space compared to the space that it's taking up in terms of the gas spreading out. So it's quite negligible in size. So what Avogadro hypothesized was that essentially, regardless of the size of the molecule or the atom, if it's in a gas, if it's in a gaseous state, it's always going to take up the same amount of space. Now he said it a little bit differently. He said equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So if you have a liter of one gas and a liter of another gas, and you have them at the same temperature and the same pressure, then you'll have the same number of particles of one gas as you do of the other, regardless of whether one gas is 10 times as big as the other. So this was Avogadro's hypothesis, and he was correct, and they eventually went on to actually determine what that volume is. And so they call this molar volume. And as long as we have a gas, and as long as it's at STP, right, you're going to start seeing this more and more, this idea of STP. And if we go back up here, STP should be apparent. It's not same, but standard temperature and pressure, right? Standard temperature and pressure. So if you have a gas and it's at standard temperature and pressure, then 1 mole of that gas will take up 22.4 liters. Any gas. It could be argon, sulfur hexafluoride, krypton, chlorine gas, oxygen gas, hydrogen gas, anything. Any gas, as long as it's at STP, then 1 mole of it will take up 22.4 liters. Which is nice, because, again, we don't have to calculate anything. We know that if it's a gas, if it's at STP, that's the number. That's the conversion factor. And then we also know that if we don't know that it's a gas, or if we know it's a gas and it's not at STP, then we can't really calculate volume unless we know the density, right? So we would have to know density and know the mass in order to do that. And we've calculated density before, so we won't go through that again. So the conversion factor will always be 22.4, but again, you have to check 2 things. 1, that it's a gas, and 2, that it's at STP, standard temperature and pressure. And if you're reading a problem, it will tell you, right? It will say, this such and such gas at STP, so you'll know going into the problem if you're able to use this conversion. And that fills in the last little bit here, right? So if you're going from volume to moles, you're going to take 1 mole divided by 22.4 liters. Right? That way the liters of volume will cancel and you're left with moles. If you're going from moles to volume, again, as long as it's a gas at STP, you can just multiply by 22.4 liters over 1 mole. Moles will cancel. You'll be left with meters as volume. Okay? So we're going to do some more practice with this tomorrow in class, but I would like you all to take a crack at these practice problems. They're actually found on page 321 in your textbook, or you can just pause the video and work them from here on the screen. Essentially, in number 21, this clever little fellow here basically gives you the path, right? In problem 20, convert from moles of gas to volume. So we're going from gas to volume, and here we're going from volume to moles. Right? So moles to volume, volume to moles, and you have your conversion factor of 22.4 liters per 1 mole. So take a shot at those, and we'll continue to work with this a little more tomorrow.